Alright, so in this video, what we're looking at is the same linear transformation from last time, but what I want to show this time is that T is a surjective map. And to sort of remind ourselves what it means to be surjective, it means that no matter which element I pick in R3, there's at least one, if not more, elements in the domain R5 that hit that R3. So if I pick a different one, then there's a bunch of vectors that map to it too, and that's going to be true of every single vector in R3. Something will hit every one of those from R5. So that's what we want to show here. In other words, what we want to show is that the image of T is equal to R3 itself. Now, whether or not the image of T is equal to R3 is fairly straightforward to determine. We just need to look at the dimension of the image. If the dimension of the image is 3, then it has to be all of R3 because it has to fill up all 3 dimensions. If the image of T is 1 or 2 or 0, that means that it is just a line or a plane or the origin in R3, and therefore definitely isn't all of R3 itself. So we want to see is what the dimension of the image of T is. And so you may recall from the last video that we've already computed the reduced echelon form of the matrix representing T, and what we got was this REF right here, which last time we used to show was that T was not injective. But for surjectivity, again, I'm looking at the dimension, and what I noticed is that, hey, look at that. There are 3 pivots here, right? And so there being 3 pivots means that this vector, and this vector form a basis for the image, right? So what this is telling me is, so the first vector corresponding to the first pivot the third vector and the last vector, or the fourth vector, these form a basis, the image of T. Thus, the dimension of the image of T is 3, and the image of T has to be R3, right? It has to fill up the whole space. Alright, so thank you very much. In the next video, we're going to take a look at a linear transformation that is not surjective. Thank you.